Hey everybody, welcome to our first video in Unit 13, which is all about the specific heat capacity of a bunch of different substances that we might encounter. Before we get into that though, what I figured we would do is just kind of talk about what thermochemistry is before we dive into all of these details about thermochemistry. So I decided to title this unit Thermochem. Well, what is it? You might be familiar, of course, with chemistry, duh, but the thermal part kind of sounds a little bit like thermometer. And when you think of thermometer, you might think of heat. And that's exactly what thermochemistry is. Thermochemistry is the study of heat energy that's associated with chemical reactions and also with phase changes. So you probably have started to hear me talk a little bit about thermochemical reactions and whether a particular reaction absorbs heat or releases heat. We're not going to dive too much in the reactions portion of it. I just want to talk mostly about phase changes. In order to vaporize water, for example, which is what this picture is showing on the screen, if I want to boil water, I have to put energy in order to vaporize a sample of water. That's why when you're going to make pasta on the stove, you have to turn the heat on, crank it up, because you want that water to get nice and hot really fast. How much energy do you need to apply to a system to get it to start to boil? That's really what thermochemistry is all about. How much energy needs to be applied to a big sample of water versus how much energy needs to be applied to a smaller sample of water. Why does it take so much more energy to bring a pot of water to boiling versus when I make my coffee in my little carafe type thing? I have like a little water heater that you just press it and it boils the water. You might have one for tea too at home. Why does it take so much less time to boil the small sample of water than it does the larger sample? That's what thermochemistry is all about. Sorry if I'm a little washed out here. I'm like closer to my window than I have been in previous videos, and I can't move my computer too much more, so we're just gonna leave it. I'm a little washed out. It's fine. You know what I look like in real life by now. In our gas law unit, we also talked about what temperature is. So I just want to differentiate temperature versus heat. So temperature is a measure of the amount of kinetic energy that particles have in a system. So if I have two gases that are at the same temperature, we say that they are at the same kinetic energy, or they have the same kinetic energy. And that's because that's what temperature is it's a measure of how much the particles are moving. And of course, we recognize temperature as how hot or cold something is. The higher the temperature means the hotter that object is, but that's because those particles have more kinetic energy. The lower the temperature, the less kinetic energy those particles have. Wow, I am really washed out. Let me see if I can move my computer a little bit. It's a really nice day today and I'm inside filming this video. Okay, so I think that's a little bit better. So that's what temperature is, whereas heat is a measure of how thermal energy flows within a system. So we say that objects can they can gain heat or they can lose heat, but we don't say that something has heat. So for example, if I have a hot coffee, right, that hot coffee transfers its heat to my hands. That's why my hand starts to feel warm or even hot, depending on how hot the coffee is. So that heat is a transfer from energy from that hotter system with the higher kinetic energy to a system of lower kinetic energy. That's what heat is. It's the transfer of energy from one to another, whereas temperature is a measure of kinetic energy. So we measure the temperature of something, and we can also measure the amount of heat that something has, or we can measure heat transfer, rather how much heat is being transferred from one object to another. And the primary unit for heat is called the joule. And you might remember talking about joules back in our electrons unit in Chem 1, where we talked about E equals H times nu, where energy is the amount of energy that particular electrons have when they jump around from the excited state to the ground state or vice versa. We also measure heat in units of joules as well. And the joule is the heat that's required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And it's different for every substance. The amount of heat that's required to raise 1 gram of water by 1 degree Celsius is very different from the heat that's required to raise 1 gram of iron metal by 1 degree Celsius. And that all comes down to not only their intermolecular forces, but also their intramolecular forces, whether or not they are covalent bonds or metallic bonds, or if they are intermolecular forces that are holding those particles together. And that's something we'll talk more about as we progress through the unit. But just so you know that the joule, Joule, is the primary unit for heat. We're going to see that quite a bit. You're probably familiar with calories. So if you look at, a candy bar or Cheez-Its or something that you're eating, on the back of that, the nutritional label tells you the amount of energy that you get from that. And that's kind of what this little thing here is showing. So if something is 700 calories, let's say a slice of pizza is 700 calories, that's a unit of energy, and we can convert how many joules of energy is that using a couple of different conversion factors. You won't have to do this, but it's always nice to kind of put into perspective what these values of joules represent. So 700 calories, one slice of pizza would be about 3 million joules. So that's why we don't use the joule when we're talking about nutritional energy, because 3 million is a lot. We use a kilocalorie, actually, which is a capital letter C. Fun fact for you. So in thermochemistry, there are 2 different types of thermochemical processes, and I want you to get very familiar with both of these. The first type of process is an exothermic process. An exothermic means that that particular system releases energy to the environment. And when a system releases energy to the environment, it tends to feel very warm. So if I look here, my system is whatever is happening in my reaction or whatever is happening in my vessel that I'm working with. So if I'm boiling water, that boiling water would be the system, whereas the surroundings would be the air that's around it. So in an exothermic thermochemical process, your surroundings will absorb heat energy and therefore they feel warm. The system releases energy and the surroundings absorb it and therefore it feels warm. That's why when you touch a hot coffee, that hot coffee feels warm, because that coffee is releasing energy to the environment. It's warming up your hand and it's warming up the air that surrounds it. Whereas an endothermic process is the opposite of that. So an endothermic process absorbs energy from the environment. In this case, your reaction vessels, your systems tend to feel very cold. So notice here that your system is absorbing energy from the surrounding environment. Great example of this is like if you have one of those cold packs that you crack them. If you get injured, let's say like an injury cold pack, you snap that little thing inside and it starts to feel cool. That particular process is absorbing energy from your body when you put it on yourself, which is why it feels cold. So the same thing is true when you we talked about the virtual lab with the isopropyl alcohol and all the different types of alcohols. Why do they feel cold when you put them on your skin? That's because in order to vaporize, they're absorbing energy from your body. They're absorbing energy from the surroundings. So in that case, they tend to feel very cold. Now you're going to hear me use the word heat a lot, but you might also hear me use the word enthalpy. And in chemistry, heat and enthalpy mean 2 very different things. But for us, because we're not in like a physical chemistry class where we're dealing with like variations in pressure and volume and whatever, for us, enthalpy tends to be the same thing as heat. So for us in Chem 2 and in a lot of even your college courses, like your organic chemistry and all that, enthalpy and heat tends to be the same thing. They're interchangeable terms. So your enthalpy is the total heat content of a system at constant pressure. What makes heat not equal to enthalpy is when it's not at constant pressure, but we don't have to worry about that. All of our calculations will be at constant pressure. And we represent enthalpy usually with a capital letter H. So just so you're aware, the heat and enthalpy are interchangeable words for us. And just to reiterate here in this particular image, This particular flask right here, whatever's in this flask, especially if this were capped right here, this would be the system, right? So the system is usually just your reaction vessel. The surroundings is whatever's surrounding that system, not including the system, right? So like we said, exothermic reactions, the system releases heat to the surroundings. So the system gets warmer, releases that heat energy to the surroundings. Whereas in an endothermic system, your surroundings release energy to the system, or the system absorbs energy from the surroundings. So endothermic system absorbs from the surroundings, exothermic the system releases to the surroundings. And that whole entire thing is what chemists call the universe, right? So every system with all of its surroundings equals the universe, which is why all of the laws as we have it today work the way that they do, which we're not going to get into that because that's a whole can of worms to open up. And like I said, at this point in your chemistry career, the terms enthalpy and heat can be used interchangeably. And again, that's because we are working at constant pressure. Makes life easy. The change in enthalpy in a system is represented by delta H. So, of course, H is that enthalpy. That little triangle is what we call a delta, and delta usually means change. So if you took calculus before, you're probably familiar with like dt over, or d whatever over dt. That d is a delta, technically, or change in something versus change in time. And in chemistry, you'll see a triangle that represents change in quite a bit. And this change in the heat in a system, or change in enthalpy, is used to describe both physical processes and also chemical processes. Like I said, we're going to talk mostly about those physical processes. Melting ice, for example. So if I go from solid water or ice to liquid water, in order for ice to melt, you need to input energy. I have to add heat to water to get this reaction to happen. So delta H is going to be positive. I would have to input 335 joules of energy to melt 1 gram of water. So notice that your delta H is positive here. And because I have to apply heat to ice, this particular reaction would be endothermic. Heat must be applied to ice in order to get it to melt. So that's an endothermic process. And when you have an endothermic process, your delta H is going to be positive. So condensing water also involves a change in the heat that's involved. So if I go from water vapor, which is a gas, to liquid water, gases have vibrational, translational, and rotational energy. In order to go to the liquid phase, they have to get rid of all that rotational energy. It's losing heat in the process. It's losing energy. I go from gaseous water that's very energetic to liquid water, which has not as much energy. For this physical process to occur, and it's physical because I'm not breaking any covalent bonds here, this is an exothermic process. So notice how your delta H is negative here. So when I go ahead and I condense water, you're producing a little bit of heat in that process. So when you take a really hot shower and you have all of that water that condensed onto your shower or onto your mirror, that process is also going to release heat. So not only is the bathroom warm in itself because you're taking a warm shower, but it's even warmer because all of that water that condensed onto the window or onto the mirror also released heat, which, where does that heat go? To the surrounding air. Therefore, the air temperature rises. Lastly, this is a chemical change, and that's because I'm breaking some covalent bonds and forming new covalent bonds. These first two processes are physical processes because I'm only breaking intermolecular forces. Notice that the chemical makeup of water isn't changing, but for the decomposition of water, I am producing new chemical bonds that weren't there previously. Anyway, let me move my little image here. This particular process also will absorb 116 kilocalories of energy because water requires energy to decompose. This is also an endothermic reaction. Heat must be applied to this system in order to get hydrogen gas and oxygen gas as products. So a major takeaway from this, if you have a positive delta H means that energy must be applied. So in your note packet, you can even write plus heat here if you wanted to. Actually, let's see if I could write it here on my screen. So we could write plus heat, writing with the thing there. So that's considered an endothermic reaction. For condensing water, heat is a product. Heat is liberated plus heat. And that's why my value here is negative, whereas here it's positive. Last one here, I do still have a positive enthalpy change there. So heat is also going to be a reactant there. So just keep that in the back of your mind as we progress through these. Well, what the heck? How do we measure the heat transfer between two substances? How do we measure the heat that occurs in a phase change, the heat that occurs when I have a hot object and a cold object and I have that energy transfer? We could do that using what's known as calorimetry. And we're going to do a really nice calorimetry lab, probably at least one actually in class. Calorimetry is a technique. Let's get my picture moved back down here. Calorimetry is a technique that's used to measure heat flow based on observing the temperature change when a substance or reaction absorbs or releases heat. And the best way to do that is really in a coffee cup, right? A coffee cup calorimeter is a really great way to just measure the temperature changes between two substances. So I have a cup right here. Here's my coffee cup. And you have an inner one and an outer one just to kind of help contain all of that heat. You have a stir bar or a stir rod that you could just use to stir right here, which doesn't usually look that fancy, but you would have something that's kind of in there to help stir it around, and a thermometer. And you would have some sort of reaction that's happening there inside of that coffee cup. And whether or not this reaction is absorbing or releasing heat, we can measure that temperature change. So if I start this reaction at some temperature, and if that temperature goes up, right, my change in temperature would be positive in that case. I'm gaining heat as a result from that. And using that temperature difference, I can convert that into heat. All right, well, if the temperature changed this much, how much energy was involved in that process? Whereas if my delta T goes down, right, if my initial temperature is higher than my final temperature, your change in temperature would be negative. And using that value for delta T, that change in temperature, we can measure heat flow between two different substances, which is what we're really going to focus on a lot. All right, we did a lot of notes, but this is one of the last slides that's on here. So how do we do that, right? How do we use that delta T in a calorimetry experiment to measure the heat that's either absorbed or released from a reaction or a physical process? We can do that by knowing the specific heat capacity. And your specific heat capacity is the amount of heat that's required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. And again, that's usually heat, like we said before. Typically, it's measured in the joule, right? And it's different for every different type of substance based on what type of substance it is. Now, the biggest equation that you have to know for this unit is this next one, right? This next one is like crucial. Like it should be like, it's like a PV equals nRT, right? We know PV equals nRT for gas laws. We got to know this next equation for thermochemistry. And this next equation is Q equals MC delta T, right? So, the animation's not right, but that's okay. So Q equals MC delta T, where Q would be the energy or heat that's absorbed or released in a reaction. So Q would be the heat, usually in joules and kilojoules and calories, some unit of heat, or of heat energy, I should say. M is the mass of the substance. If I have a very large sample of something, it's going to release or absorb a lot more energy than a smaller sample. So the mass of that does in fact matter as well. And that's what lowercase m is. C is your specific heat capacity, and this depends on the substance and what phase it's in. So you will either be given this value or you will have to calculate it knowing all of the other variables. So we're going to get some practice here in a second with specific heat capacity. And delta T, like I said, if delta H is your change in enthalpy, delta T is your change in temperature. Remember that triangle is always a change in. And we represent the change in temperature as final temperature minus the initial temperature. So it's final minus initial. And this value is usually given to us in degrees Celsius. Sometimes you might be given the initial temperature and you might be asked to calculate the final, or you might be asked to calculate delta T as a whole. What's the change in temperature? Just depends on the particular question that it's asking. So here's a list of a whole bunch of different specific heats for some common substances. Let me get the pen out here. Let's see if we can show you, take some notes, because I want you to really see some very important things. Let's look at the top here. Top one is liquid water. So I have water solid, liquid, water solid, which is ice, of course, and then I have gaseous water right here. So all of these are just H2O. And notice that I have a specific heat value, or a C. So this is specific heat, otherwise known as C, right? C in Q equals MC delta T. And it's different for that particular substance and that phase. So liquid water has a very high specific heat relative to ice and even relative to water vapor as well. Ammonia is a pretty high specific heat as well. It's 2.09. Benzene is a liquid. Looks like I have ethanol as a liquid and a gas. Notice how pretty high these values are. I mean, it's kind of like, okay, what do we compare this to? Well, these are high when I compare those to metallic solids. Look at these, right? So I have aluminum, which is a metal. Calcium is another metal, not carbon. This is actually a covalent network solid. But I do have copper, that's a metal, gold, iron, mercury, lead, all of these ones that I just put little stars by, these are all metals. So a star indicates it's a metal. Why do these have such low specific heats? Because these have metallic bonds, and metallic bonds are characterized by that delocalized sea of electrons, which conduct electricity and heat. So because your metals have that delocalized sea of electrons, they're constantly moving throughout the system. It's very easy for metals to raise or lower their temperature. It does not take a lot of heat to raise the 1 gram of aluminum by 1 degree Celsius. It takes barely any energy to raise the temperature of gold by 1 degree Celsius. And that's because it already transfers energy very well. It transfers heat very well because of those metallic bonds. Up here, these are more molecular solids, right? Whereas molecular is comprised of a lot of nonmetals. Molecular solids are held together by intermolecular forces of attraction. Those do not have free electrons that can conduct electricity well, or that can conduct heat very well. So as a result, it takes a lot more energy to raise the temperature of 1 gram of a molecular solid than it does to raise 1 gram of a metallic solid by 1 degree Celsius. And this goes all the way back to that last unit, which deals with the types of solids and intermolecular forces. And that's why chemistry is so great, because everything starts to really come together once the deeper you get into it. Something else to keep in mind before we get started with some sample problems here. Like I said before, when heat is being absorbed into a system, so if you have an endothermic reaction, your Q is going to be a positive value. Whereas when heat is being released from a system, your Q is going to be negative. And that's because it deals with that delta T. So whether or not your final temperature is larger or smaller than your initial temperature. And we're going to get some practice with this in a second. Let's go ahead and do the sample problems in the notes. I think there's 3 of them. We did quite a bit of notes in there today, but it's a lot of background information. So let's dive in and do some Q equals MC delta T problems.
Okay, so let's do these sample problems together in the notes. We're just going to do 1 through 3 today. So the major equation that we have to keep in mind, remember, is that Q equals MC delta T. That is so important in this thermochemistry unit. So we're going to use Q equals MC delta T. Of course, where delta T is your change in temperature, and that's usually represented by the final temperature minus that initial temperature. And something else that we need to remember is that value of Q, which is what we just talked about on that very last slide. But Q is going to be either a positive or negative, depending on whether or not your final temperature is greater than or less than your initial temperature. So Q is going to be a positive value when heat is absorbed. So we'll say heat is absorbed in the system. So a great example of a system or of a process that would have a positive Q value is if I am melting ice. So if I'm going from ice to water as that process is melting, we have to input energy to that system in order to get ice to melt. So in that case, Q is going to be positive. That would be an example of an endothermic reaction. Whereas Q would be a negative value if heat is going to be released. So Q is a negative if heat is released. So like we said before, a good example of that would be like if I have water vapor that's being condensed into just water. We're just talking about physical changes for most of this this section, not so much chemical changes. The reason why our Q is negative is because our final temperature is actually less than our initial temperature, right? So because our initial temperature is much higher than the final temperature, we are going to get a negative value for Q. So let's say that our final temperature is 20 and our initial temperature is 50. 20 minus 50 would give me a negative value. Whereas if Q is positive, our final temperature is greater than our initial value because I had to put energy in order to raise that final temperature. So that's why we have these different values for Qs, and we just have to keep those in mind as we do some of these practice problems. So sample problem 1, calculate the amount of energy that's required to raise the temperature. So because I'm raising the temperature, we can infer that Q is going to be a positive value. And we don't have to necessarily figure that out for this one because we're calculating the energy. We should get a positive value. But it's always good to just recognize whether or not it will be positive or negative. We know our mass, so the mass of the sample is 14 grams, and I'm raising that by 3 degrees Celsius. Notice it's not giving me an actual final temperature and an initial temperature. It's just telling me that I'm raising it by 3 degrees. So I don't have to do any subtraction here because that is delta T. My change in temperature is 3 degrees Celsius. And we're given that specific heat of water. Like I said, you'll always be given this value if you're not calculating it, knowing all the other variables. But your specific heat of water is 4.184. All you have to do is plug the numbers in and solve. So Q is equal to, because Q is what I'm trying to find, calculate the amount of energy required. Mass of the sample is 14 grams. Specific heat for water is given to us. That's 4.184. Units for that number are joules per gram degrees Celsius. And my delta T is 3. So all I have to do is just multiply all of those values by one another, and if you do that correctly, you should get positive 176 with units of joules. units happen to be joules because if I look at my specific heat, my units for specific heat, grams is on the denominator here. And if I multiply that by the mass, that cancels out the grams. And same thing here, because degrees Celsius is in the denominator, that cancels out with my degrees Celsius and my delta T expression. So I'm just left with units of joules, which you could see is represented right there. And that's it. All you really have to do with this equation is learn how to manipulate it, which can be tricky, but that's why I'm here. And that's why we're going to do a whole bunch of labs. We'll do a whole bunch of problems with these. Number 2, calculate the heat required to raise. So again, I'm raising it. So we know Q is going to be positive here. Q is positive. 5.39 grams of water. Looks like that's the mass. And I do have a change in temperature here, but I do have to calculate that delta T. So I'm changing it from 21 to 33.7. So my 33.7 is my final temperature because that's what I'm bringing it to, whereas 21 is my initial. I'm not given C because, well, we just did an example with water, so the C is going to be exactly the same. Otherwise, again, we're just going to plug it into Q equals MC delta T. Q is what I'm trying to find. That's equal to the mass, which is 5.39, times the specific heat of water, joules per gram degrees Celsius. Only difference here is that I have to actually plug in my final minus the initial. So my final temperature is 33.7. And it's initially at 21. So when you subtract that, because your final temperature is greater than your initial, you should end up with a positive value, which gives you a positive Q, which makes sense because I have to input energy to raise the temperature of water. If you calculate this correctly, you should get 286 joules. So if we compare this value to like the amount of energy that's in a slice of pizza, like we said, a 700 calorie slice of pizza, one slice of pizza has 3 million joules, right? Whereas we're talking about 286 joules. So when we're comparing these energy values to like food energy, these are so minuscule compared to the amount of food calories that we need to sustain ourselves. And let's try this last one here. A little bit different because we are going to calculate the final temperature. We want to know TF in this example. So TF is what we're trying to find. When 1,250 joules of energy is removed. So this is important right here because typically your questions will not represent your delta H as positive or negative. You have to infer whether or not it's positive or negative. And because we're removing 1,250 joules of energy, that must mean that Q is negative 1,250 joules. And that's all because we're removing that much energy. So just be careful because those negatives can really get a little tedious sometimes. I have the mass and I have my initial temperature of the water, which is 50. So let's use Q equals MC delta T again, but in this example, I do know Q. So Q is negative 1,250 joules. That's equal to 6.39. Still working with water. You will have some other examples where you're not working with water, but I guess the notes, I just decided to keep it consistent. We're trying to find the final temperature if I'm starting at 50. So if I'm removing this much energy, my final temperature should be lower than 50. And if we calculate that, we should in fact see that. The way I like to do this is I like to just kind of isolate this guy first right here. And I do that by multiplying this whole section first. And then I'll divide it by what's over here. So when I do that, I get a value of negative 46.8. And I'm going to set that equal to TF minus 50. I like to just kind of take it step by step for these because it is very easy to get tripped up on just the math. Solve for final temperature. I'm going to add 50 to both sides, and you should find TF is equal to 3.2 degrees Celsius. Now, if you didn't make your Q negative, you would have gotten a temperature that is higher than 50. And that doesn't make sense because if I'm removing that much heat energy, it has to be less than that. It's not going to be more. So just be careful with your positives and negatives as you're working through these problems. As always, if you have any questions, please make sure you take notes in your note packet. Bring them to me next time you see me. But we will get quite a bit of practice with this in class and in the couple of labs that we're going to do. I hope this video made sense, and otherwise, I will see you in the next video. Bye.